Thank you. So as you've heard, my name is W.Hearn, and I'm a PhD student at Chalmers University of Technology. At Chalmers, I'm part of the Center for Additive Manufacture Metal, also known as CAM2, which focuses on powder and process development for a variety of AM technologies. And what I'll be presenting today is sort of an overview of some of the work I've done during my PhD, which is focused specifically on the development of structural steels for laser powder bed fusion. Now, currently, the use of structural steels in LPBF is quite limited, and this stems from the relatively high carbon content of these alloys. This carbon content leads to an issue with processability because the carbon within your cooling austenitic phase has insufficient time to diffuse uniform carbides due to the rapid cooling conditions that you have. So what happens instead is, as you have your rapid cooling, the carbon within your austenite becomes entrapped at octahedral sites of your FCC austenite lattice and induces the transformation to the distorted PCT structure of martensite. Now, this martensitic phase is very hard and brittle and creates material that's highly susceptible to fracturing. And as you probably all know, it's a problem in LPBF materials because there's also noticeable residual stress in your material that come about due to the rapid solidification conditions that you have, in addition to this volume expansion you have of your martensitic phase. And so the hope when you want to develop this alloy is you want to try to find how can we mitigate this cracking issue, either by changing your alloy composition or your processing parameters. And that's sort of what I'll be covering today. So I'll first talk about the process development that we did to try to find high density crack-free specimens. I'll then talk about, and this is why it fits into the session, how the in-situ tempering that the process of LPBF provides allows us to achieve this. And then finally, I'll be talking about the mechanical property performance of these alloys when you're able to make them high density and crack-free. Oh, yeah, and just to quickly show you, this is the nice big cracks you have in these materials. So it's, you know, a little bit of a problem. But to actually carry out this, this analysis, we looked at a variety of materials. We first started with 6 plain carbon steels going from compositions of 0.06 to 1.1 weight%, so pretty large range there. We also looked at 3 low alloy steel specimens. These were specifically the 4140, 4340, and 8620 grades. And there you had carbon contents. Oh, oops, click the button. Going back. Okay, perfect. Back on track. We went from about 0.2 weight% up to 0.43 weight% carbon. And these were pre-alloyed gas adamance powders that were supplied by Höganäs and Sandvik respectively. Now, to produce these powders, we used 2 different machines. The first was an EOS M100 machine, which we used for initial process development of both the carbon and low alloy steel powders. We also had an EOS M290 machine, which we used for secondary process development for the low alloy steels, as well as the production of the mechanical property specimens. And there are some differences between the machines, but the major one we focused on was that the M290 allowed us to preheat the build plate up to 180 degrees Celsius. And then finally, in terms of the parameters we looked at, we produced for both of the machines and materials specimens at DEs of 60 to 200 using a set laser power, patch spacing, and layer thickness. And for the specimens produced on the M290, we also produced these specimens at preheating temperatures of 25, 100, and 180 degrees Celsius. So jumping into the first part, I'll talk about the kind of process window we saw for these alloys. And generally for the carbon and low alloy steels, the density of your specimens was related to your volumetric energy density. I think it's quite well established and would follow this schematic that you see here. So we found specimens produced at low energy input would have very poor specimen porosity, as you'd have these many large and irregular pores that related to lack of fusion porosity. These are some very nice partially sintered or unmelted particles inside them. In the same way, when you go too high in your energy input, you also have a pretty poor specimen density, but in this case, instead of your large irregular pores, you're having more rounded pores that when you do some nice etching, you see the bottom melted boundaries and clearly are related to keyhole-based porosity. And then kind of finally in between that, you have your sort of sweet spot of process window where you're able to make relatively pore-free specimens that have densities of 99.8% or greater. Now, The porosity within your specimen was also influenced by the build plate preheating temperature you had. Specifically, it affected the formation of lack of fusion pores when you had low energy input. So in this case, for the 4140 alloy that we had, you see that as you increase your preheating temperature from 25 to 180, you're having a reduction in lack of fusion porosity of about 2-3%. And you can also see that from the cross sections here, as you increase your preheating temperature, the size and number of your lack of fusion pores decrease. So I've covered your quick stuff about porosity. I think it's quite well known, but you can see there's this crack that's still there. And so I'll now talk into how the parameters affect that kind of defect. And why they form in these alloys, as I said before, depends on your carbon. This is because carbon not only affects how easy it is to form martensite, so your hardenability, but also the hardness of the martensite itself. So just very easy to see. For the carbon steel specimens, increased carbon, increased hardness of your material, more likely for fracturing. Now, in terms of the processing parameters, they also had an impact, but their impact was dependent upon the alloy composition you're looking at. So when you had specimens with relatively low amounts of carbon, so below 0.38 weight percent, regardless of the energy input or build plate reheating temperature we used, we don't see cracks. And this is just because at this composition, your material is ductile enough to accommodate any residual stresses and avoid these cracking issues. When we start going a bit higher, so about 0.38 to 0.75 weight percent, you see that cracking is happening in alloys, but only in ones produced at low volumetric energy density, as well as low preheating temperatures. And as we increase either of these factors, we see that jumped ahead again. Okay, there we go, perfect. So you see not only the size, but the number of the cracks generally diminish as you increase your VD. And eventually when you use a high enough parameter, the cracks go away. Now the reason why this is happening is that increasing either parameter, you're improving the in-situ tempering of your material. And you can see this quite easily just from hardness measurements, where as you increase your preheating temperature or as you increase your volumetric energy density, you are having an increase in situ tempering of your material, and that is what is allowing us to avoid this cracking problem. And then when you go really high in carbon content, so 0.75 weight percent or greater, we didn't look at preheating temperature, but just from the energy input, we couldn't get crack-free specimens. So when you start going really, really high in your carbon content, you need to have a combination of both high energy input and likely high build plate preheating. But kind of what I want to get at here is that very clearly you see that despite cracking being, not prevalent, but present here, you are able to, avoid these issues by improving the in-situ tempering of your material. And the in-situ tempering provided by build plate preheating is quite straightforward to understand. You're just having an elevated ambient temperature during processing. This helps to both relieve residual stress as well as improve tempering of your martensitic structure. But the one I think is a bit more interesting is this thermocycling that's been touched upon quite often by previous authors, and this kind of heat treatment that happens as you're increasing your volumetric energy density. And so that's what I'll be talking about now. But before we can talk about in-situ tempering, we have to understand what's the initial state of martensite in this material during the process. And generally, the martensite that first forms, it will happen during layer melting. Of course, as you usually would do, you have your laser scanning across your powder bed. Everything heated above the liquidus temperature forms a liquid melt pool. Pretty straightforward. But since this material is dominated by the solid state transformation of martensite, the important aspect is looking at the portion of material that's heated above your austenite stability temperature, as this will first form to austenite, then rapidly cool and form your untempered martensite. And while I don't have operando results to show you, it's actually quite easy to see this untempered martensite even with postmortem analysis. And you can do this by just looking at the top layer, because this layer is not reheated during the process. And looking at this iron 0.45 carbon alloy, you first can very clearly delineate this portion of material from the rest after etching, as it comes out as a white layer. Then when you start doing hardness measurements here, you see that it has a very high hardness of about 750 to 800 HV, which is what you would expect in a quenched material of this composition. We then started looking in both SEM and TM, and what we see is a very fine lath martensite structure, but there's no clear presence of any precipitates. We then did further work with atom probe tomography, and what we see is that as we saw with SEM and TEM, you do have carbon atoms, and they're somewhat segregated to specific regions in your material, like phase boundaries and dislocations, but there's no formation of any carbides. So what you see in the process is that, as you would sort of expect, your martensite is in a quenchlite state where there's some segregation of carbon to different boundaries. And I'll very quickly say that if you're wondering what this is, it's just metal oxide. Now, to look at what's the tempering that happens during the process, we found that the most kind of important or the biggest change in tempering happens just below where your untempered martensite forms within the heat affected zone of your melt pool. And as it makes sense, everything that's heated below your stability temperature of austenite will reform into martensite and will instead become tempered. And in a similar way, we looked at the regions just below the top layer. And what we see already there, substantial decrease in hardness, depending on your processing parameters. So instead of 800, you're between 400 to 500. You then look at both SEM and TEM, and now you have noticeable precipitation of carbides throughout your material, specifically cementite carbides that are very small, about 30 to 60 nanometers. And again, when we start looking at APT, we see that you have, again, these cementite carbides located, and they have precipitated at the previously carbon-enriched boundaries of your material. So essentially, the kind of micro-tempering that happens within your heat-affected zone induces extensive carbide precipitation that helps you reduce the kind of the hardness of your material and its susceptibility to cracking. And how this relates to increasing your energy input is that we found that the level of your micro-tempering within your heat-affected zone would increase as you increase your volumetric energy density, as the hardness in the regions just below for the specimens would decrease by up to 20 to 25% as you increase your energy input. And the reason for this is, I think, also somewhat straightforward. You just look at the size of your top layer or your melt pool you're forming. And I think other works have covered this much better, especially with operando work. But as you would expect, as your melt pool gets larger, the rate of heat dissipation slows down. You're inducing a longer kind of solidification time, which allows for greater tempering of your material to occur. So it's this unique in situ tempering effect of the process that actually allows us to produce these types of quote unquote non-volatile alloys crack-free by the process. So now we know how to make a high density crack-free material. How do they stack up when you start actually testing them for mechanical properties? And so we conducted mechanical property testing for the low alloy steels that I mentioned, and we just produced them at the highest preheating temperature because that gave us the most stable processing range. And we also tested them in orientations vertical and horizontal to your building platform. Okay, so that's out of the way now, and I can talk about all these bar charts and what they mean. Basically, I have all the different alloys with the different orientations, and the blue boxes relate to the ASTM standard for each of these alloy grades. And what we see is that in the as-built condition, first looking at, say, the yield strength in UTS, we're achieving, I'd say, fairly good values that, of course, depending on composition, range from about 1,200 to about 1,500 megapascals. You also, at the same time, are achieving relatively high elongations that are between 14 and 15%. And if you see those values in relation to the standards for these alloys, they either meet or exceed what you expect. And what was kind of more interesting was the impact toughness, specifically the Sharpie impact toughness, where you're having, let's say, relatively high values for what would be considered a brittle material. And the other thing I want to quickly mention is when we start comparing the vertical and horizontal specimens, while there is directional anisotropy present, the level is much below the 10 or 20% that's usually mentioned in literature. One of the reasons why we're having this combination of high strength with decent ductility and toughness is, again, due to this tempered martensitic structure you have. We have very fine precipitates that are related to carbides within your material. So it's this sort of combination of properties that this is part of the reason why you're getting this nice balance between the two. You do also have a hard to see but underlying cellular structure, which also has been shown to provide strengthening effects in other alloys, specifically 316L. I think I'm running slowly on time, but the last point I want to bring up is I mentioned before you have lower levels of anisotropy when you're comparing. So the difference between vertical and horizontal specimens was only about 5 to 8%. And that primarily is due to the martensitic transformation itself. Because when you quite often look at the grains and texture that forms AM alloys, you have your standard long columnar grains with a preferred orientation. And depending on how these grains are loaded, you're going to have better or worse properties. But when you look at these materials, as you can see very clearly, you're forming this very fine lath structure of martensite between 1 and 5 microns. And the growth of martensite is not dependent upon your thermal gradient or direction of heat flow. They're going to grow athermally into a bunch of different variants that are more dependent upon the size of the parent grains or the composition of your alloy. And even if we look at the parent grains, so the kind of high angle grain boundaries, they also don't have necessarily just long columnar grains, they have a mixture of the two. So this is one of the major reasons why we're having that limitation. So I'm finally to the end, keep it very brief. What I just wanted to hopefully you take away from this is that you can produce structural steels, high density and crack free with the process. This is due to the unique in situ tempering the process provides, from tempering within your heat affected zone, as well as preheating. And then finally, you've got a nice combination of strength, toughness, and ductility due to the unique microstructure of tempered martensite. And I'd like to acknowledge Camp 2, our funding partner, NOVA, as well as our industrial partners, Sandvik and Beganes.
Thank you.